Hello everybody. Today in this video we're gonna do one very useful exercise for using the fsolve to calculate the bubble and dew point of a mixture of benzene, toluene, and xylene. This exercise was done before in the Microsoft Excel series, and I'm gonna revisit this exercise using Matlab, and we will compare the results of both. But this is gonna be very useful because there are some points that we didn't mention because we didn't go through before in the previous videos. So I thought it's gonna be useful to do this exercise so that we know if you want to make kind of complex file that uses the fsolve, how we're gonna do this. But before we go through the solution, I will quickly revise the calculations and the background of this exercise so that you feel kind of familiar with what we are doing. Let's say we have a phase diagram, an ideal system of binary system. This is the temperature versus the concentration, and then you would find that the curve is split into three parts: the liquid and the vapor. This is single phase, and this is single phase. And this is what we call the wet region, which is consists of liquid and vapor, and it's bounded by vaporous curve at the top and the liquidous curve at the bottom. And this region is of importance or of interest to us because at this point or at this region the two phases split into two, or the mixture that we have splits into two mixtures, liquid and vapor, with different compositions. So it's very useful for flashing, for distillation, or any other method of separation that depends on the difference in boiling points. So it's important for us to know how to get the vaporous curve and how to get the liquidous curve. And to do this, we pick any concentration or any composition, let's say this, and then we calculate a point that lies on the liquidous curve and the point that lies on the vaporous curve. We call this a dew point and we call this a bubble point. And it's important for us to know how to calculate these two points to know exactly what is the envelope of temperature that is gonna be useful for us to do the separation. Otherwise, you would get a single phase, no separation will take place, and then you cannot get something out of this. So to do the calculations, I'll skip this. We depend on some equations, the Antoine equation, or I mean the Dalton equation, and the Raoult's law, and by combining these two equations you can get something. But from Raoult's law, again, you can visit the video in Microsoft Excel series. It includes all the details in case you need them. I just don't want to waste time on saying something that I discussed before. So this is the vapor pressure, and the vapor pressure can be calculated from many equations. We usually use the Antoine equation. It's very famous and kind of reliable equation. And for every component I, it has A, B, and C, which are three constants for each component. And this is the temperature in Kelvin, and you calculate the vapor pressure in millimeter mercury. This is for the values of A, B, and C that we are using. You can find other variables for the equation that are fit with another set of units. Anyway, so we use the equilibrium relation that at the pressure at the gas phase equals the pressure at the liquid interface, and then we apply the two equations, and at the end of the day we get this equation that relates the composition on the y of the vapor phase, which is y, to the composition of the liquid phase, which is x, and it's multiplied by this ratio between the vapor pressure to the total pressure, which we call K. This equation can be applied to any system, either it's ideal or non-ideal. What we do here is for ideal systems. However, for non-ideal system, the equation would take the same shape, but the K would be calculated from a different way. you would get some activity coefficients and fugacity coefficients and other variables to get the or to account for the non-idealities in the system. Anyways, we will apply an ideal system today just to make the life easier, and then this is what we're gonna do. And to do the calculations for flashing, we or for the bubble and dew point, again, you can check the video for the derivation and to know how the derivation is done. But anyways, you would find that the equation relates y to x is a function of k, and k, as we said, is the vapor pressure divided by the total pressure. So the k is a function of pressure and function of temperature. And actually what I want to do from this calculation is to get the temperature at which the liquid would lie, or the mixture would lie on this curve. And that's why you need to apply to assume a value of temperature and then calculate k, and then from the k you calculate y, and from y you need to check if the t is right or wrong. And you do the check by getting the summation of y. If the summation of y is equals 1, then it's okay. If it's not, you have to reassume the bubble point. And the same thing for the dew point, but in the dew point you know y and you calculate x, which is the difference between the bubble and dew point. Anyways, so we did this before using Microsoft Excel, as I told you, and here are the values of the Antoine constant for benzene, toluene, and xylene. This is the equation that we use to calculate the vapor pressure, which is Antoine equation. This is how we calculate the K, and this is the equilibrium relation y equals K x. I'm using the same feed compositions. I'm gonna use the same pressure, and just to check, this is the bubble point 345 and the dew point is 361. What we did, we used here a solver to do the iterations. By changing temperature, you get the sigma y equals 1 here and sigma x equals 1 here, and this is exactly what we're gonna do in Matlab. So I have just to save some time, I have here the givens, which are the feed conditions, the pressure and the x feed, Antoine A, B, and C for the three components. This is benzene, this is benzene, this is benzene, then toluene, 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 xylene, xylene, xylene. And now we need to go step by step. So the first step is to first calculate the K, or let's calculate vapor pressure first. First I need to put the percentage to make a note, and then the vapor pressure is calculated from Antoine equation, and as we said before, to do the fsolve we need to use function handles, and this is what I'm gonna do. I'm gonna start because the variable is the temperature and it has to be transferred from the vapor pressure to the K and then to the sum x and y. So I'm gonna start by calculating the K as a function of t, so it's gonna be a function handle at t, and then I would say that this is exponential of Antoine A minus Antoine B divided by Antoine C plus t. And here there is no problem. The only thing that you need to keep in mind is that you need to do the elemental division, so that because you have here arrays and you don't want to make any mess. So this is the first part, and I can kind of, so if I run the file, I could see that K here is a function handle. I have Antoine constants, the pressure, the x feed, nothing is a problem. I can kind of check the vapor pressure by calculating K of, let's say, 300, and I do the run, so it's calculating the values here. To kind of check it to make sure that everything is right, I know that benzene evaporates around at 80, so it's gonna be 353 Kelvin. So it's almost 760 millimeter mercury. So it's kind of a very good way to check if you're going right or wrong. And I personally prefer to do the checks regularly, so I don't write like 10-15 lines without checking if I can do that. just to make sure that the step that you leave is fine. There is nothing that is gonna build up on a problem. Anyway, so I have now the K is calculated, and as we said, this is not the K, I'm sorry, this is the vapor pressure. Okay, so this is the vapor pressure. And from the vapor pressure, I want to calculate the K, and we said the K equals the vapor pressure divided by total pressure, which is this. And I think for now everything sounds nice, but this is the point where you would get the first error, and the error is in this. And it says that something is related to the function handle, and it tells you that something is wrong with the division. And actually, it's not the problem with the division. The problem here is that you have the vapor pressure is a function handle of temperature, and you want to make K as a function handle of the vapor pressure, which is a function of temperature. So it's going to be a function handle of a function handle. And to make Matlab understand that, you have to put the function handle here, and you might think that it is solving the problem now, but if you run the file, it would seem right. However, if you want to say you want to calculate K of 353, it's going to give you an error. And this is because the T is here, but you cannot see any T here. It is embedded in here because this is a function handle of T. But MATLAB does not understand that. To make it understand it, so you have to write it this way. So you have to make this as a function handle by putting this, and to tell MATLAB that the temperature is in this variable or in this function. And now if you run the file, you'll see that you can calculate the K. So this is a very important point. It took me a lot of time to figure out how to do it. So I hope you do not spend that much time doing this same thing. Anyway, so I now calculated the K. And then the next point or the next step is to calculate the X and Y. So this is calculating the vapor pressure and K's. And I already did that, and then I want to calculate the X and Y's. And to calculate the X and Y's, you need to use the equation. So I'm gonna calculate X for the dew point and Y for the bubble point. So I would call it YY equals K. And then multiplied by, and of course you need to use this now because you're multiplying a matrix by matrix, and of course this has to be a function of T, and this is gonna be a function handle of T, and this K of T multiplied by the X feed, and then XX of T equals a function handle of T, and then X feed divided by K of T. Okay, so now I can do the same thing. I can YY of 353 and XX of 353, and I will the file. Something is wrong. It is in the T. Oh, I'm sorry, I shouldn't put this here. It is a mistake that yeah, so now you can see you can calculate the Y's and X, and you would notice that the sum of this is not 1 and the sum of this is not 1, and this confirms that you are going right because you are just putting any number. It does not satisfy the two equations or the two sums. So now you can do the sum X equals function handle of T, which is the sum of XX, and sum of Y, sum Y equals function handle of T, sum of Y of T, of course I forgot it to put it here, and then I can do the last step, which is the fsolve. Again, I want to check that nothing is wrong here, so I put some x of 353 and some y of 353 and run the file. Everything is fine, so I have no problem now. The last step is gonna be doing iterations, and by doing the iterations I want to do fsolve, and by doing fsolve I would calculate t bubble, which is fsolve, and for the bubble point I want to make sure that the sum of y equals 0. And just to make sure that you do not write the equations wrong, we will do the fsolve on some x and some y, and fsolve would make the equation equals 0. That's why I need to put this equals. I know the sum needs to be equal to 1, but the equation is not gonna go to 1 if I do the fsolve. That's why you want to make sure that this minus 1, which is 0, will go to 0 when I do fsolve. And I would do some y. The initial value would be, let's say, 300, and that's all. So I can run the file. It says 345. Let's check. It is 345.095, so it's exactly the same number. You can do the same thing for the t due is gonna be the same thing here. It's gonna be some x. So now it's 361. So I know 345, 361.21, exactly the same values. Of course, you can do some kind of stuff that we did before, like putting the options equal optim set and then display none. And we did this here, like put the options and put options just to show the values here. And of course you can use fprintf or use anything that you can use to display this as a text, and we did this before, so I'm not gonna waste more time doing this stuff. You can do it by yourself, and it's gonna be a good exercise to like do multiple things in one file. So the file now is done, and you saw it is not a complex file. It's very simple. You just need to make sure that you know how to put a function handle in another function handle. The second point is to make sure that you put this equal to 0 by putting -1 here. And if you check the steps, exactly the same step we did here, this x feed, we did the vapor pressure, and then k, and then y, and then sum of y, and then and then sum of y, and then the solver. And I personally I believe that this is going to be easier to use because you do the run once for both. However, here you had to do the solver once for this and then once for this. And anytime you change any variable, you had to do the solver again. However, here I know it might be kind of difficult to track. It's not as easy to see as here, but it is more quicker to do the calculations and to do everything without repeating many steps to redo the calculations. One thing that we will visit later is that you can use this to calculate the bubble and dew points at multiple concentration, and this is something that Excel will not be able to do. You can use a for loop and repeat the calculations, let's say 10 times from 0 to 100% or whatever the range of concentrations that you're interested in, by just adding some lines to this code without need to do more calculations. And this is one point of strength in Matlab that Excel cannot compete with Matlab in. So I'll stop for now, and I'll see you in the next video, inshallah. Goodbye.